by the distributive laws. These are the things we have. 0a is equal to, in place of 0 we can write 0 plus 0, and by the distributive law this can be written as 0a plus 0a. Now I could have started with this, and similarly a0 let me write a0 plus 0, that is actually equal to a0, and a0 can be written similarly like this. And using the, here we have used the left distributive law, and here we are going to use the right distributive law. Note that if you prove 0a is equal to 0, from that you cannot conclude that a0 is also equal to 0, because it's not given that the ring is commutative, it's a general ring. Okay, so we have to prove the two things separately. a0 plus a0. Now, by the cancellation laws in the additive group R, we have recall the left cancellation law and right cancellation law, that is that we already have in the group R under addition. By that law I can cancel 0a from these two sides. Here also I can cancel a0 from two sides. So finally I have this 0a equal to a0 is equal to 0. So that means in a general ring, if I multiply any element by 0, in whatever order I want, the end result is 0. Now we come to the second one. Okay. By part 1, so by the previous part, AB plus minus AB, which can be written as A plus minus A B. What have we used here? The right distributive law. And this is 0. And we know that this is equal to nothing but 0. And this is where we are using part 1. But but 0 can also be written like this: AB plus minus AB. Right? So by the left cancellation law, in the group R, we have, that means we now have AB plus this is equal to AB plus this. So we cancel AB from both sides, and we have this minus A times B is equal to minus A. Oh, I should carefully use bracket here. What is the meaning of this? This is the additive identity of the element AB. Okay, we should not confuse among the different things that are possible here. I mean, of course, once we prove this, they will be the same. We can just simply write minus AB without using brackets. But for now, this means the additive identity of AB. That's why this plus AB is equal to 0. So we have got this. Similarly, one has, similarly means now you know how to prove the other one. One has A times minus B is equal to minus AB. Note that we cannot change the order. We cannot write, here we cannot write B times minus A because we are not given that R is a commutative ring. Okay, so this ends part 2. Now we come to part 3. We have by part 2 the following: minus A minus B is equal to minus A times minus B. Note carefully what we are writing. Again we apply part 2. This is equal to minus AB. And this is equal to AB. Okay, what have we done here? Here for us, we are able to write this is equal to this, where minus A is minus A, that is fine. Minus B is considered as a single element, like how we consider B here. So that's how we get this one. Again, using A and minus B, this directly follows from the previous part. Now, why is minus of minus is equal to AB? Do you see why? It's because AB is an element in the additive group R, and this minus AB in that additive group, in the notation of general group theory, is nothing but AB inverse. And from group theoretic result, we already know that this is equal to AB. So that's how we get AB. Okay, so this gives us 3. Next, now we additionally assume R as a unit element 1. Then we need to prove this, right? Minus 1 times A is equal to, then again by part 2. Minus 1 times A is minus, that means the additive inverse of 1 times A, and since 1 is the unit element, 1A by definition of a unit element is A. So that's how we get this. This follows from part 2, that is, it follows from here. In bracket we write, take A equal to B equal to 1. So what shall we have? No, not part 2, part 3, sorry. We take A and B both 1, so we get the left hand side here. On the right hand side we have 1, 1, which is nothing but 1. So that's how we have this lemma. So this lemma allows us to do some calculations like how we ordinarily do calculations with real numbers or with integers. Okay, so let me just write the comment here. So we shall henceforth calculate with 0 and negatives like we always did. Always did means like how we do with integers or real numbers. We denote the element a plus minus b by a minus b. Okay, the meaning of a minus b is actually a plus minus b. In fact, in case of integers or rational numbers or whatever numbers we are familiar with from our previous experience with mathematics, this is how a minus b is defined. Okay. Now, although this lemma is nice and it's useful, it's not something very difficult, and it also does not say anything deep about rings. In short, it's not very exciting. Now we are going to go to the exciting results. One such result will now be presented. But before we present that result, we mention one principle which is very easy, which we are going to use in the proof of that result. And that is the pigeonhole principle. If n objects are distributed over m places and n is greater than m, if the number of objects being distributed is greater than the number of places where the objects are going to be put, then at least one place receives at least two objects. It's like, for example, say we are distributing 5 objects over 4 places. No matter how we distribute it, there will be at least one place which will receive at least 2 objects, simply because the number of objects is more than the number of places. An equivalent statement is this: if, and we shall use this equivalent statement every now and then, not just here but sometime in the future also. If n objects are distributed over n places, here the number of objects and the number of places are the same, such that, but there is a condition, no place receives more than one object, then each place receives exactly one object. That's how we are going to use this principle. Now we state the result. So this is the second lemma, right? So this will be lemma 3, 2, 2. A finite integral domain is a field. Let me refill this, okay? Then we will continue. So if we already have seen the definition of an integral domain, it's a non-zero ring that is commutative and has no zero divisor. Now if such a structure is also finite, then it has to be a field. Now this is not as obvious as the previous lemma. Okay, it has to be proved. Although the proof is not very difficult, but this is certainly more difficult than the previous lemma. And it's also not immediately obvious how one can go about proving this. But we will see soon that there is an idea that can be used to prove this. And this is where I understood that the definition of an integral domain in the book has to be rectified, because according to the book, I mean, if you don't rectify the definition of an integral domain to make it a non-zero ring, then this lemma says that the ring consisting of only the zero element is a field, which is wrong. Why? Because according to the definition of a field also from this book, note that I have not changed. A field is a commutative division ring. And do you remember the definition of a division ring? In a division ring, the non-zero elements must form a group under multiplication. So which is not true in case of the zero ring, we have already seen. So that's why I had to change the definition of an integral domain, and I understood that Herstein made a mistake here. Okay, so now let's look at the proof. Let R be a finite integral domain. Let R be a finite integral domain. Since it is finite, we can list its elements let it have n elements, where n is some positive integer. Being an integral domain, R is already commutative. So we have to show that the R has a unit element and every non-zero element has a multiplicative inverse. Now I have already said that definition of a field is wrong, but keep in mind that for us, since R is an integral domain, it is by definition a non-zero ring. So now I just need to show that it has a unit element and every non-zero element has a multiplicative inverse. Now there is no problem. So that's what we are going to do now. First of all, we will show that R has a unit element. Let A not equal to 0, be any non-zero element in R. Consider the elements ax1, ax2, ax3 up to axn. These elements, okay. Note that if we assume axi is equal to axj for some integers I and j, I could have written j less than or equal to I, but without loss of generality I am writing this. One of them will be less than or equal to the other. If I assume this to be the case, that is what I am trying to say here is that if this list collapses, if there are some repetitions in this list, then a times xi minus xj is equal to 0. Okay, let me write why this is 0. axi minus axj is equal to 0. Note that in this calculation, I have not only used the distributive law that I have in the ring R, but the previous lemma also, because I have negative sign involved. So when I will multiply minus xj by a, I actually have a times minus xj. That is nothing but minus axj. That comes from the previous lemma. So so if I assume this, then I have this. And since a is non-zero, we have xi minus xj equal to 0 or xi equal to xj or I equal to j. Okay, so if I am assuming this, then I have this product equal to 0. But keep in mind that R is an integral domain. So in an integral domain, we don't have zero divisors. So in particular, A cannot be a zero divisor. So since A is non-zero and the product of A and this other element is 0, the other element has to be 0. Otherwise, by definition, A will be a zero divisor, and integral domain has no zero divisor by definition. So that's why this other element must be 0, which means xi must be equal to xj, and since these are distinct elements in R, I has to be equal to j. Hence, ax1, ax2 are distinct, or I may write are n distinct elements in R which has n elements. So by the pigeonhole principle, these are nothing but these elements. The elements ax1, ax2, etc. Okay, my handwriting is becoming more and more of the elements account for all the elements of R. That is, let me write in this way also so that it becomes more clear. A x n. So R is equal to this set, R is also equal to this set. It does not mean that x1 is equal to ax1. The order may be something else. Then what do we get from this? Since A belongs to R, so A will also be a multiple of A, some multiple of A. If I call these elements multiples of A, since A belongs to R, we have A is equal to AX, I may call it let me call it K. Herstein uses I naught, but let's not complicate matters more. A is equal to AXK, which is also equal to XKA for some K lying between 1 and n. Keep in mind that we are in an integral domain, so it is commutativity is there with us. We claim that xk acts as a unit element in R. That is, we have to prove that if we multiply any element of R by xk, we are going to get that element back. Let y belonging to R be any element. Then y is equal to axj, which is equal to xja for some j lying between 1 and n, because that's how the elements of R look. Hence, we are interested in this product yxk. Y can be written as axj, right? And we have xk, or I can also write, instead of writing axj, I can write xj a. Now by associativity of multiplication, I have xj axk, and axk is nothing but a, and xja is equal to y. So this indeed acts as the unit element in R. You can say the unit element or a unit element, it does not matter. Once a unit element exists, it is unique. We have already seen that. And note one more thing, that here we have yxk equal to y equal to xky. Okay, that also should be kept in mind, because in a non-commutative ring also there may be unit elements, and in proving that in a non-commutative ring an element 1 is a unit element, you have to make sure that 1a and a1 are both equal to a for every a. If you just prove that this is equal to a for every a, it's not, then 1 is not necessarily a unit element. In this case, this need not be taken care of because already we have commutativity. This proves the claim. So that means our ring has a unit element. Also, since now 1 belongs to, okay, this proves the claim since xk, shall I write it as 1? Yes, let me write. Now I have the right to write this xk, denote this xk by 1 because it is the unit element. Now since this also belongs to R, we have 1 equal to xk equal to AB equal to BA for some B belonging to R, because 1 will also appear in this list, so 1 will also be a multiple of A times something else, and that something else is nothing but the multiplicative inverse of A according to the definition of multiplicative inverse. This shows B is equal to A inverse, and hence R is a field. Okay. Now, okay, so that completes the proof. Keep in mind that if we don't change the definition of an integral domain the way we have done, this becomes a field which is not true. That problem is now not present anymore. Now this result has an immediate corollary which is very interesting, and the corollary goes like this. I can write the corollary here. For any prime number P, the ring of integers modulo P, Jp, is a field. Note that we have already seen one such field in our example J7, the integers modulo 7. There we directly verified that it is a field. However, now this will come as a consequence of this lemma, not just for 7 but for any prime P. So JP, you see, JP is a finite commutative ring. If we can show that it is an integral domain, then it will be a field, and that's exactly what we will show now. For that, we need to show that JP has no zero divisor. Proof. By the previous lemma, it's enough to show that JP has no zero divisor, where we already know that JP is a commutative ring which is finite. That I am not mentioning here. Let A and B, these congruence classes modulo P, are being considered such that their product is 0. Then what is the definition of this product? AB, that is AB is congruent to 0 mod P, or P divides the integer AB. Now recall our result from the previous chapter, not the previous chapter, but from the study of integers, the third section of the first chapter. If a prime divides the product of two integers, then it divides at least one of them. Then something can be written about the reference, then by the corollary to that lemma, but you understand what I am using here. Then P divides A or P divides B, that is A is congruent to 0 mod P, or B is congruent to 0 mod P, that is, continuing this, A is congruence class containing A is the 0 congruence class, or this shows that if A is non-zero, note that we have not assumed anything like that here, we have just simply assumed that the product is 0. Now if A is non-zero, then B has to be equal to 0, because you see, according to this implies A and B, at least one of these should be true. Now if